This paper tackles the problem of creating relightable and animatable neural avatars from Sparse-View, or monocular, videos of dynamic humans under unknown illumination. Our method takes only a Sparse-View, or monocular, video as input and reconstructs a relightable and animatable neural avatar under unknown illumination, which can then be relit with arbitrary environment lights and animated with arbitrary motion sequences. Recent neural scene representation-based methods have demonstrated the ability to extract detailed geometry and photorealistic appearance of human performers from Sparse-View videos without sophisticated studio setup. Albeit showing the capability of novel pose synthesis, the reconstructed avatars in these works are either not relightable as they bake the shading and shadow into the appearance model or not animatable as they bake the human motion into neural networks. Given world space camera arrays, we perform sphere tracing on the hierarchically queried distances, sector 3.2, to find surface intersections and canonical correspondences. Light rays generated by an optimizable light probe are also sphere traced with HDQ to compute the closest distances along the ray. Material properties and surface normal are queried on the canonical correspondences and warped to world space. For soft visibility, then, the final pixel colors are computed using the rendering equation. Given the world space query point x, we approximate its world space distance to the closest surface point on the neural avatar with the hierarchical distance query algorithm, which is later used for sphere tracing. The query algorithm consists of 4 stages: A. Coarse distance query, B. Inverse warping, C. Fine distance query, and D. Smooth distance blending. Since we use a discrete light probe, the visibility term for every light direction needs to be integrated on the area of the pixel, which is time-consuming. Thanks to the global meaning of distance field, this occlusion and integration process can be approximated using distance field soft shadow, DFSS, producing soft visibility with a single light sample. We adopt the microfacet BRDF model for our material representation, which is composed of a diffuse albedo term and a specular roughness term. Using the hierarchical distance query, the canonical correspondences, surface normal, albedo, and roughness values can be easily obtained from the world space SDF of the neural avatar under arbitrary human poses. We optimize our relightable and animatable neural human avatar by rendering the image with given camera poses and comparing the pixel values against the ground truth ones. Due to the ill-posed nature of the problem, we adopt a 2-stage training strategy and add additional regularizations: 1. The geometry and material. We compare our method with baselines on the synthetic human dataset. Following Relighting 4D, the SSIM and PIPS metrics are computed in the bounding box of the human region, while the degree of normal and PSNR metrics are computed within the foreground mask. Due to the inherent scale ambiguity in the inverse rendering task, we align the rendered images and albedo with ground truth ones following before computing metrics. Since NOR factor is designed to fit static objects, we train and evaluate it only on the first frame of each sequence. Asterisk operator denotes variance without the normal and visibility MLPs. As shown in the figure, our approach can successfully decompose the material and dynamic geometry of the neural avatar, generating a relightable neural avatar from only Sparse-View, or monocular, video inputs. In comparison, NOR factor trained on one video frame overfits the training image with Sparse-View input. Relighting 4D passes structured latent codes to NOR factor's MLPs, enabling it to relight a dynamic video of human performance. However, its quality decreases greatly when synthesizing novel poses. Here we visualize the reconstructed geometry and material properties from the Sparse-View video input with unknown illumination. Note that our method not only preserves the geometry details and successfully makes them animatable, the wrinkles on the trousers, but also recovers relightable material properties from such limited input. After reconstruction, we can then relight and animate the neural avatar. Our method can also handle monocular inputs. Even with such limited input, our method can still recover the geometry and material properties of the human and make them animatable and relightable at the same time. Given new lighting conditions and novel human poses, our method successfully integrates the neural avatar onto the new environment. Relighting 4D fails to handle the novel human motion and on the SDF fails to factor in the novel environment map. Thanks for watching.